So now we're going to go into ligand binding association. We have our Ka, or association value, which is a function of the amount of bounded O2 over the separate concentrations of the protein and the ligand, which we're going to use O2 in this example. So again, you have the PL, this is the bounded oxygen, and these are the separate concentrations. So this is your protein, and this is your ligand, which is going to be O2. And your protein is either myo or hemoglobin, just depending on what we're using. So globin's for the protein, ligand, oxygen for the L, and then this is oxygen bound to protein. In the cell, there's a high concentration of L, or ligand, so we can treat the concentration of ligand as a constant. So this will not change. Then we need to talk about fractional saturation, which is denoted by the letter Y, a capital Y. It stands for the number of binding sites occupied over the total number of binding sites in the molecule, so unoccupied and occupied binding sites. And we can express that using the concentration of bounded oxygen over, again, the concentration of bounded oxygen plus the concentration of protein. So this value itself is hard to measure. Excuse me. So instead, we're going to change this into this, where we have the concentration of our ligand, which, like we said, would be a constant, over the concentration of the ligand plus 1 over Ka. So Ka is the association constant, and that is this function right here. So basically, it's just the inverse of this in the denominator. So relationship between association and dissociation. So associations, basically, you're going to have your parts unbounded to binded. So I think of my two puzzle pieces to like a complete puzzle. Dissociation is the opposite. It's going to be, bounded molecules to the parts that are unbounded. So breaking the puzzle. So association, I'm making the puzzle, I'm associating my puzzle pieces. Dissociation, I am breaking my puzzle, they no longer know each other, they are dissociating from each other. So for Ka, that value again is the amount of binded ligand over the separate concentrations, and then Kd is just the inverse of Ka, so it's the separate concentrations over the number of bounded ligand. So here the Y value would change to be the ligand concentration over the ligand concentration plus 1 over Kd. So basically the inverse of this, which is just Ka. Yes. So the units of association and dissociation are slightly different. For Ka, if we are using units of m, or molar concentration, this can be micromolar, nanomolar, like molar 10 to the -5, whatever, it just depends. We can use m to describe them all. For Ka, it's going to be 1 over m. And then for Kd, it's going to be m. So the units 1 over m for Ka, just m for Kd. And that just has to do with the fact of the way that the fraction is set up. If you were to take each concentration value, which all these would be in molar concentrations, and you just added them together, like this would just be 1 molar concentration, and these you would have to multiply it, so you can do molar squared. We don't know what the values are. That reduces to 1 over m, and then here it's just the inverse, so m squared divided by m just equals m. And then we can have this free Gibbs energy equation that we can use, especially with the KEQ. So the relationship between Y, or the fractional saturation, and Kd and also Ka is this. So when the concentration of ligand equals Kd, that is when 50% of the ligand binding sites are occupied. So when we have this value at Y, 0.5, and wherever, if we draw a line from 0.5, wherever our curve hits that line, that is our KD value. And our KD value, again, is when equal to Y at 50% is basically the concentration of when 50% of like embedding sites are occupied. And that is also in the function of inverse, so it's 1 over Ka. Dissociation constants can vary in magnitude. A lower KD value means there's a higher affinity for the ligand or for the protein, so it's more willing to bind, it's binding more strongly, there's a minimal amount of dissociation happening. The binds are very tightly wedged together. There is very little tearing them apart. Now, with a higher KD value, that means there's a low affinity, which means that the binding is not as strong and they're easily broken apart, and there is more dissociation. So this is just a table of values describing that. All right, and then for an example, we were given this graph and then we were to read it. So we had to figure out what are the dissociation constants for A and B, and then we know that is KD when the concentration of L is equal. So that's going to be at 0.5. We can just draw a line and then find out where our curves hit that line. Here for A, it's 2, and then here for B, it's 6. Now we know that if it binds more tightly, we're going to have a lower KD value and a higher affinity. So the compound A is going to bind more tightly because it has a KD value of 2.